So first of all, I would like to say a big thank to the organizer for the program and for inviting me here. But I would also like to say a big thank you to the speakers of the previous days, because I learned a lot in the past 2 days. And so I just want to give a big thank you to everyone. So this is the title of my talk, but because the audience I am speaking to here is quite different from the one I'm used to, I decided to change the title just a little bit, because I need to tell the story backwards than what I tell it. So basically I'm switching the 2 keywords here, and I will start with the first one, but I'm going backward the usual way I do it. Let's see if it works. I hope this will make it clearer for the audience. Okay, so why are radioactive nuclei important to build up habitable planets? Here is one of the most important examples, the aluminum-26. It's a radioactive nucleus with a half-life of less than 1 million years. And here you can see a plot from a paper from last year from Tim. This is a very nice plot because it shows what is the difference when you build planets like the Earth, if you have aluminum-26 or if you don't. So if you look on the left of the figure, is bluish. This is the case where there's no aluminum-26 or very little aluminum-26. And if you accrete the planetesimal to make planets like the Earth, while you accrete them in this specific scenario to make these planets, of course, but while you accrete them, you keep the ice that they have inside. You don't lose water, you don't lose ice. So you accrete and you end up like with planets that have a lot of water, so it is like ocean planets. But let's say instead you are in the solar system where there was a lot of these nucleus there when you were making these planets, or even cases where there is more than the amount that was in the solar system, then in this case you can see that at the same time as you accrete the planetesimals, you also heat them up and dehydrate them. So they lose water and you end up with planets like the Earth. So in one sense, we were lucky to have all these nucleus in the early solar system. And I want to explain in a little more details why this heating effect happened from the nuclear point of view. So how aluminum-26 is producing heat? So on the left side of this slide, you can see a very simple nuclear structure of what happens when the aluminum-26 decays. So it decays into magnesium-26. So basically the nucleus turns protons into neutrons and lose a charge, a positive charge. But the angular momentum of the aluminum-26 nucleus is too high to allow it. It's this J equal 5. So it cannot decay straight into the ground state of the 26 magnesium nucleus. So you can think of nuclei in the same way as the atomic structure. You have shells with energy levels. And what happens is that the aluminum-26 instead decays into an excited state of the magnesium-26 that has a similar J number. And then it is the magnesium-26 that immediately decays onto the ground states and release a very high energy photon. Now, this is the high energy photon that releases the heat in these first protoplanets that we showed. It has then the impact on the production of planets like the Earth. So the big question here is where the aluminum-26 came from. Because it decays so quickly, it's not easy to have it around. So it must have come from somewhere in the early solar system. And then the connected question is, because of the big impact that it has, do we find the same nucleus in other systems or not? This is the big question. And there are a lot of answers, unfortunately too many answers, so I will try to give an overview of what we know of the possible ideas to explain the origin of this nucleus. I will focus in this talk on this stellar origin hypothesis, and this is the idea that the aluminum-26 came from a star external to the solar system. So something in the environment of where the solar system was born. This is a hypothesis that can be divided in two typical scenarios. One is the more traditional local scenario. So there was a nearby dying star, maybe a supernova, that injected this nucleus in the sun while the sun was being born. But because this is a scenario that comes with some problems, for example, it's not very easy to have a star that is dying right next to a star that is born, then some people in recent years, they have thought more about something like a global scenario. So, which would be a bit more natural, possibly, because it would imply that the evolution of the gas in the galaxy or in the cloud in general was enriched in the aluminum-26. So maybe you don't need a special event, a special case for the solar system. So these are the stellar origin hypotheses that I will mention here and explain in a bit more details. But there is also the solar origin hypothesis, which I don't discuss here because it will be shown in the talk after this one. I just want to mention the basic idea here is that the nuclear reaction that produced aluminum-26 did not happen inside a star, an external star, but they happened inside the solar system thanks to fast protons and helium that can also interact with solid and gas and make 26. I just want to mention that there are two general main problems with these other possible solution. One was shown in the first time in 2007. This is a plot from the paper from Duprat. And the problem is that the maximum mass, the maximum total number of aluminum-26, or the maximum mass that bear aluminum-26 in the solar system is quite low. So you can produce locally high amount of aluminum-26, but if you want to try to explain the widespread presence of this nucleus, then it's hard. And you can see in the plot, the y-axis show the maximum mass in masses that would bear aluminum-26, but what we need to match is the minimum mass solar nebula component, and you see there is a factor of 10 problem here. And the other problem is that you don't only produce aluminum-26, you produce also other nuclei. For example, beryllium-10 is very, very efficiently also made by this process. So typically, the beryllium-10 is the top line here. And you can see that you produce too much beryllium-10 and too little aluminum-26. This is just to highlight the fact that we don't have a ready solution yet, and we have to really try every possible way. So this is still a way that could work, but has problems. But it leaves open for me the fact that I should still also look about the stellar origin hypothesis. We have to look into everything at the moment. Okay, so this is the stellar origin hypothesis. I already made some difference between a local and global scenario. But here we have a problem with the literature, I think, because there is a huge number of papers trying to solve the aluminum-26 problem. And this huge number of papers generate a lot of, I think there is a lot of confusion about what actually the scenario proposed are. And sometimes people who want to start reading some of these papers don't realize that each paper is a very, very specific case. And it's difficult to find paper unless they are reviews that cover the whole picture. So one has to be very careful. And to scare people a little bit into when they try to look into this very, very hot field, I prepared this other slide where I tried to to classify the literature in the different type of ideas that they are proposing. So as you can see, I could find 7 different scenarios when I put the different pieces, the different type of the number of sources, the timing of pollution, the type of source. So if we start from the top of this diagram, you see the number of sources. Multiple sources is basically the global scenario I mentioned before. So it wasn't just one star, but a lot of stars enriching the gas or the D score. The single source is more like the local source, that there was one star responsible for the aluminum-26. But then this is not the only thing we can divide the different papers in. We can also look at the timing of the pollution. When did that happen? So we had the idea that maybe these multiple sources already polluted the initial gas is a primordial pollution. So the gas from which stars like the sun form is already naturally enriched in aluminum-26. So this is the part on the far left of the diagram. Or on the far right, we have what people call the early injection. So what happens is that the aluminum-26 is injected at the same time as the source is triggering the formation of the nebula. And this is quite typical of this single source scenario. But then in the middle here, we have a late injection case. And here again, the formation of the sun, the collapse of the nebula is not connected with the injection of the radioactive nuclei, but the solar system already formed, there is a disk, and then the aluminum-26 is injected. But then I have to choose the type of source, which was the star responsible for the pollution. There are many stars that can make the aluminum-26 in the galaxy. Which one should I choose? Here I'm focusing only on stars that are massive, because because we need stars that are around star-forming regions. Stars in star-forming regions don't live long enough to have long-lived stars in them. So typically people focus on massive stars, stars of masses higher than 10, say. But even if we only focus on this one, so here I am removing all the literature that doesn't focus on this one. There's more literature that I'm not putting here. Even if I only focus on this one, I can eject aluminum-26 in the wind phase of massive stars before they explode, or when they explode. So again, I have to split everything another 2 times. And after I do this, I find 7 different types of explanations. And this is a bit to try to make people realize of how complex is this topic and how difficult some order in all this, and also how there's no consensus. You can see that all these scenarios are still looked after these days. Some of them started in the 70s, but there's still paper that followed them last year or 2 years ago. So we are totally not having an answer. And the other issue here is that if we want to not only understand the solar system, but every other stars, if they have aluminum-26 or not, each of these scenarios will give us a different question to the answer if the other extrasolar system have aluminum-26 or not. So it has very, very deep implication which one we decide to be the correct one. Okay, so I don't have time in the next 10, 12 minutes to explain all the scenarios. I'll give you very briefly a few examples. Example of the local case. This is a famous case, a single supernova triggering the collapse of the pre-solar cloud core, and while doing that, injecting material with a shock wave. There is a long series of many papers by Boss et al. I think they reach maybe paper number 8 on this topic. So it's very, very well investigated if you want to check this scenario. And here is just an example. On the left side, there is a pre-solar cloud core and a line representing the shock wave coming. In the middle, you can see the shock wave is getting through and it's triggering the collapse of the cloud. On the left side, it's possible to see a disk already. If we look at the disk on the mid-plane, there's the density picture in the middle, and on the right, the shock wave material. It is important that we need to mix the shock wave material with the disk, because that's the material that carries the aluminum-26. If we don't mix it, then the aluminum-26 don't end up in the early solar system. And these models are showing that this works. You can mix the aluminum-26 in there, so it is a viable model. But every supernova model comes with a big problem, because I'm focusing on aluminum-26, but we need to be careful because it's not the only radioactive nucleus that we have in the early solar system. These are, I put in red here, two other famous ones, especially ion-60. It's another famous radioactive nucleus. It's also a heat source, by the way. And manganese-53 is very well known to have been present in the early solar system. If I take a typical mass, a typical supernova from a star of a 25 solar masses, which is considered as typical for this scenario, and I take the predicted ratio that I plot in the x-axis, divided the early solar system ratio, which is what I want to match, I normalize such as I get for aluminum equal 1, so I get the right amount. You can see that I get 1,000 times more ion-60 that I need, and maybe 300 times more manganese-53. This is a typical supernova problem. These are typical supernova products. And it's the reason why people are starting to think that maybe it's better to use winds, because winds from very high mass stars, Wolf-Rayet winds, so you have to go, say, about 30, 40 solar masses to have already winds, strong winds before the supernova. These winds, they can eject aluminum-26, and they don't eject absolutely manganese-53 and ion-60. So they are ideal to solve this problem. And so people have looked also in the local scenario about this type of winds, and they have imagined a scenario where the sun was born. This is in the left side, a very simple schematic image. It's just a cartoon, basically. So there's a circumstellar dense shell, which is the purple bit in the cartoon, and the sun is forming in this shell. And the shell is due to the interaction of the winds of the Wolf-Rayet star and the molecular gas cloud. The problem here is not as much investigated as much as the supernova. So we don't actually understand if the material from the cloud is mixing inside the early solar system and how. So this is treated as a free parameter, a free injection value, fraction. Some people are proposing, and this is to the right, that there's dust grains in these winds, which is a bit speculative, debatable, and these dust grains somehow they manage to then to penetrate the gas, and then the solar system can form, reaching aluminum-26. Briefly, a couple of examples of the global scenario. This is a paper that has received a lot of interest. It's from a couple of years ago, because it was looking at the galactic interstellar medium. We're not even inside the star-forming region, but I think the resolution is quite high. Like, to model the whole galaxy, it is high resolution for the whole galaxy, but maybe it's down to a few parsecs resolution. These are chemohydrodynamical situations, so very, very state-of-the-art. And here is the plot where on the y-axis is the aluminum, and on the x-axis is the ion-60. And it shows the probability contour of the composition of newly formed stars. As you can see, most of these newly formed stars would have a lot of aluminum-26 and a lot of ion-60. This is the red, darker region in the plot. But the early solar system value, I point out here with the red arrow, is about at the end of that arrow there. And this is outside of the main density contour. It would tell us that the sun formed in a sparse region as a special case. It seems quite of a rare situation. And the problem, it's kind of funny here, because it's not the problem of having not enough aluminum-26. There's a lot of stars full of aluminum-26. The problem is that you also have the ion-60. So the sun is special because it's low in ion-60, not because it's high in aluminum-26. Yeah, I'm not I don't feel too comfortable with the idea that the sun needs to be special yet, even if it's only one event. So, but this is the situation. And there's another example of the global scenario, which is a very nice paper from 2013. This time, the simulation focused on giant molecular clouds, the evolution of giant molecular clouds, not of the galactic interstellar medium. And you can see here the top panel is the evolution of aluminum-26, the bottom panel, the evolution of ion-60 in time. The gray dots are dense star-forming clumps. The yellow lines are individual stars. Again, to have aluminum-26 high is not a problem. There's plenty of these stars that show aluminum-26. But then they also have ion-60, way much more than what we see in the early solar system. So the sun has to be special again, but for another reason. And this is, again, is the usual supernova problem of making too much ion-60. It comes up in the local scenario, it comes up in the global scenario. And so either there was one special supernova, we can imagine some ways to repress production of ion-60 in supernova. And in this case, we have to do something a bit special, a bit of fine tuning, I would say. Or some people have tried to get rid of supernova in this global scenario. And imagine, for example, that the supernova ejecta are thrown out of the molecular clouds because they're too fast, but the winds are slower, and so we keep the winds. Or maybe we only can see the evolution of the very massive stars up to 25, higher than 25 solar masses. And these stars, they don't go supernova, they do a collapse direct into a black hole. There are several ways we can solve this problem, and people are considering all of them. What I am doing to try to address this problem is try to look at it from another point of view. And this is where I go into the chronology. I can use radioactive nuclei. Not only they are heat sources, they are also very precise clocks. And the interesting thing is that if you look at the bottom here is the aluminum-26 I've been talking about so far, the ion-60 I mentioned, manganese-53 I mentioned, but there are many, many other radioactive nuclei that we know were present at the start when the sun was born. And this is not even the whole list. And we have data, so this is the fourth column here, that's the data that come from the analysis of meteorites that have very high precision. I can use these numbers. They are not heat sources, but I can use them as clocks. So what time do I want to try to measure? That's the question. What would help me to understand a bit better the environment of the birth of the sun and therefore the origin of aluminum-26? If I look very schematically at the history of the matter that ended up in the solar system, I think I can divide it in two phases. The phase at the left is the evolution of the Milky Way galaxies from when it was born to the time when the sun was born, 9–10 billion years. And here we have thousands, hundreds of stars, hundreds of thousands of stars that they're born, they died, and when they die, they eject new chemical elements in the interstellar medium, and we have new stars. But then there's a moment where the material that ended up in the solar system must have been incorporated into a star-forming cloud. And from the birth of the star-forming cloud to the birth of the sun, some time could also have passed. So if I can measure that moment in time when the star-forming cloud was born, maybe I can understand something better about this, what was exactly the star-forming cloud. And I can do that just using the exponential decay of these radioactive nuclei. I know their abundance at time t0. That's from the analysis of meteorites. if I can predict their abundances at the time when the star-forming cloud form, then basically the difference in their abundances is exactly the same thing as the difference in time. That's the beauty of this decay, of the radioactive decay. So what we are doing is trying to characterize the evolution of radioactive nuclei in the Milky Way galaxy within the context of the cycle of matter in the Milky Way galaxy. So you have stars that are born, then they live millions, billions of years, then they die, supernova, they merge, they do different type of supernova, they do winds. And when they die, lots of these stars, they eject stable isotope and also radioactive isotopes back into the interstellar medium, and we have the cycle again and again. For the radioactive nuclei, this is more difficult because they also decay. I cannot just pile them up. So, and the problem is that these stellar events are not continuous. I don't have a continuous injection rate, but it depends on when the single star dies. So what we end up with is some zigzagging, because it's a balance between how long it takes nucleus and how long it takes it to decay. So we have to study these using statistical methods, which is what we're doing. Again, I already ran off my time, so I try to be brief, and I don't have the time to explain all this method, but you can look at our papers. Here I just show one very special case where we assume, for example, that the radioactive nuclei that we observe only carry the signature of one last event. So we're trying to build up the time scale that the time scale of the matter that ended up in the solar system. From rapid neutron capture isotopes, we can time the last neutron star merger event to about 100 to 200 million years before the formation of the solar system. You can see this in the paper we have done this here. The last low mass giant star is come from slow neutron capture nuclei. We time it to about 20-40 million years. And then I can try to time the last type 1a supernova event from manganese 53, but I can have a little bit of manganese 53 from core collapse supernova inside the cloud. So this is only an upper limit. And just to finish off is a little bit of fun. What can I do with this information? So far, I have not found any cell-consistent solution that gives me an isolation time less than 10 million years. What would in the context of star formation, if I can characterize the time scale that passed from the birth of the star forming region to the birth of the sun, I can tell, for example, that the sun, if it was born 10 million years later, it must have been born not in the first or in the second stellar group that formed. This is just a very specific case, but it must have formed later within the cloud. So I can tell from when the star formed to where probably the sun was born, and so what kind of environment it was feeling. And this is at the moment just for fun, because I don't have a clear answer yet about this time that elapsed. But we're working on it. And so just as a quick takeaway message, I hope I convince you that we still don't know the origin of aluminum-26 in the early solar system. I am trying to use independent constraints from other radioactive nuclei to understand the environment of the sun birth. And we need stellar nucleosynthesis and the evolution of the Milky Way galaxy. We need to understand them properly if we want to understand these questions. And I just want to say that the aluminum-26, if it came from the surroundings, it was a gift and not a threat for the solar system, because it helps us to make the Earth. Thank you.